I want to start today by just recalling a little bit about what we did the week before about the BV complex and antifields and how they impose the equations of motion. And then I want to move on to look at the B res T complex, which will impose gauge invariance in a homological way. Suppose B is a vector space, or indeed a manifold, algebraic variety. And polynomial function. The BV complex is defined if we take xi, the coordinates on V, we introduce the polynomial ring as xi, but also some new guys, psi I, where psi I are of degree -1. They're fermionic, so they're anti-commuting. And the differential is at the classical level it's this. So I differentiate my action, and that's just a function of the x's, and I put that next to the operator of differentiating with like this fermionic variable. And what this does, the image of this is, things like that. So the cohomology of this, at least H0, will produce for you functions on the critical locus of S. Then there's a quantum correction which is an order 2 differential operator. And we saw last time that we can interpret this whole thing as being divergence for the functional measure. H0 of this is classically functions on the critical locus and the quantum level it's functions on V modulo divergence where we use the functional measure. So because of this, at the quantum level, it really captures things about the functional integral. And it's worth remarking that although this is I feel it's kind of a physical physics thing to give these kind of ad hoc and confusing names to things. In mathematics, you would call this the derived critical locus. When h bar is 0. So that means the cohomology of this whole complex so what it computes so there's an old construction due to Serre of constructing what's called the derived intersection of two algebraic varieties. This constructs functions on the derived intersection of the zero section with the graph of ds inside the cotangent bundle of D. Okay, so the classical critical locus is ds is a one form, so I take the image of that one form is some submanifold of the cotangent bundle. The critical locus is where is that zero? Where does that intersect the zero section? And there's a procedure called the derived intersection, which produces for you a D manifold. And this simple case, this derived intersection construction is due to Serre. And it turns out to match the CV treatments. Yeah?
In the last slide, is H bar formal variable or just
here? H bar is, I want to treat it normally as a formal variable. I suppose in this context, working in finite dimensions, it's probably okay to treat it as a number. But in infinite dimensions, we should definitely treat it as a formal variable. Okay, so the BRST complex. So this is another piece of kind of standard homological algebra, which is turned into physics, but becomes a bit more confusing when physicists. Suppose that V has an action of a Lie group. And which leaves S invariant. So this is the finite dimensional version of having gauge theory. And if we want to consider the integral over the quotient, so what we'd like to do is to treat this integral in a homological way similar to this. So there's going to be two steps. First one is we will treat the quotient and then we'll consider the critical locus best that the quotient homological. And more generally, when we quantize it, we'll consider the divergence, the image of the divergence with respect to the functional measure in a homological way. So this way of treating this quotient homologically is called BRST. And here, when we do both things together, we might call this BRST/BV or just BV. But like for the mathematicians, everything will be, people who are familiar with derived algebraic geometry, this is just what you do in derived algebraic geometry. We take the derived quotient, and then we take the derived critical locus. So how do we do one? Well, whatever the quotient is, the functions on the quotient, so the quotient is like the set of G orbits, so the functions on it must be invariant under the action of G. So functions on the quotient is going to be the G invariance in functions on Phi. We let G be the Lie algebra of this group. So we'll choose a basis. And move some structure constants. And these guys will act by some vector fields on this manifold. So, forward. So this is a TA acts by vector fields, say F X I A E X. So these are some polynomials of the x's, so vector field of polynomial coefficients, and these must commute according to the structure constants. So when I commute these vector fields in the usual fashion. So the invariants they're going to be those polynomials phi of x such that zero for all a. So there, these vector fields send these functions to 0. Any questions? So the simplest case to think about is all these functions are 1, in which case g acts by translation. The next simplest case is all these functions are linear, in which case the Lie algebra acts by some linear representation. It could be quadratic, in which case it might act by conformal transformations, and so on. So we want to impose this equation homologically. So there's a formula for how to do this, which was worked out by Chevalier and Eilenberg, this was in the 50s, I suppose. So it's called the Lie algebra quotient. The invariants are imposed homologically by the Lie algebra quotient. So what's that? So this is, as a vector space, it's the symmetric algebra on the dual of my vector space and through the exterior algebra on the dual of my Lie algebra with some differential. the Chevalier-Almer differential, well, so that means, so I have my original fermionic variables, my original bosonic variables, the x's, from the symmetric algebra. The new fermionic variables, Ca, given by the dual of the Lie algebra. These are fermionic in their degree 1. So they have the opposite grading to the antifields. So these are the ghosts. And the Chevalier-Almer differential, also called the BRST differential, although these guys did it 20 years before, is given by the formula so to impose this equation for every A, so we want to have like the kernel of this differential to be given by those B's satisfying this equation. So I want to have something like this, right? So the first term will be sum for I and A, C A, F I A, X E X I. But if you look at this, you notice that it doesn't square to 0 because the commutators of these vector fields, if I look at the square of this term, because these are fermionic, the square will be antisymmetric in these indices. So there'll be antisymmetric here, and there'll be commutators of the vector fields. Okay? And the commutators of the vector fields satisfy that equation. They're not 0. So we need to add on another term to make square 0. And the other term is this kind of universal term, which always appears involving the Lie algebra structure constants. And it's CA, CB, E by C, half times the structure constants. Okay, makes sense? And now we can check that this guy squares to 0. So I'm not going to go through everything, but we can just stare at a bunch of terms that will appear in the commutator. So one of the terms will be, so one term, if I square this piece, I'll get something like C A, C B, F A, C, F I C, E by dxi. Call this alpha, and this term beta. This is the alpha term. Now the alpha beta term will also look exactly the same, because this guy will contract with that guy. Then I'll pick up an FABC. But with opposite signs. Careful about it, and they'll cancel. And similarly, the beta term, this is going to be equal to 0 by the Jacobian. In fact, the vanishing of this term is equivalent to the Jacobian. Because if you compute it, there's going to be some F, and you want it to be totally antisymmetric. Okay, any questions about this? So for mathematicians, this may look like completely ad hoc. We're just making it up. But actually, there's a really clean homological meaning to this. So this complex computes or harm in the category of G representations from the trivial representation to this ring of polynomials. So why is this good? Normally, maps of representations from the trivial representation to something, those are the invariant elements. But if we like homological algebra, we never want to take HOMs, we want to take the derived HOMs. And this is one particular way of computing the derived HOMs. So that's why it's a good. And we can also write this as the X self X over the universal enveloping algebra of G of the trivial representation. Okay. So this is kind of why we should think of this as a good homological model. Let's see. So one important point we'll come to later is when we're dealing with gauge theories, this might be some huge infinite dimensional Lie algebra. It's very far from being a simple algebra. So that means, if we took a simple Lie group, the operation of taking invariance, that's a very nice operation because I can just integrate over the group, reject the invariance. But for an infinite dimensional Lie group, I can't do that. So there really are non-trivial derived functions in this Lie group, so it's important to do this. Okay, so let's explain an yeah.
Can you elaborate on that a little bit more? Like how is the taking derived variance to the Lie algebra related to taking variance in the Lie group?
Yeah. So there's a map one way, but it's generally not an isomorphism. So if I have a compact Lie group, so if G is compact, then the functor which sends a representation to its invariance is exact. However, the Lie algebra cohomology of G with coefficients in B is equivalent to the invariance tensor, the cohomology G. So just the invariance tensor, the cohomology of the group of B is a manifold. So in this case, they're really different. And you can see why that has to be the case, because like here we use the fact that it was compact, but the Lie algebra doesn't know about which form of the group we've taken. That could have taken a non-compact form, in which case this would not be a mixed. There'd be different category representations. So when we work in infinite dimensions, typically what you find is an infinite dimensional Lie algebra, which looks like it jets into a finite dimensional. So it's an extension of a finite dimensional simple Lie algebra by something nilpotent. If I have a nilpotent, for a nilpotent algebra, there's no difference between the Lie algebra and the group. So for all this infinite dimensional nilpotent stuff, the Lie algebra is good enough. And this is the right thing to do. For the simple part, which corresponds to constant gauge transformations, we have to think a little bit about which form of the group we should take. Does that help?
Yeah.
Okay, any other questions? Okay, so let's see how would we impose gauge invariance for a gauge theory. suppose we have a gauge theory on Rn. So the fundamental field is in one form on Rn. I want to take the gauge group to be U1 or R. So, and we want to impose gauge invariance at the level of operators in this homological way. So what are the operators we find? So naively, we find O I of A is the ith component of A evaluated at 0. In other words, I contract with the vector field. So I want to be kind of careful at this stage in distinguishing between a field, which is something on a which is some continuous thing on the manifold satisfying some differential equation, and an operator, which is a function of this. This is like one of my pet peeves with terminology in physics. So, you know, a long time ago, Maxwell said a field is a function on space-time. And then at some stage in the, you know, I don't know when, like if you look at the Whiteman axioms, he uses the word field for a function of what Maxwell calls a field. And so it's super confusing. And it's, I mean, it's okay when you have a metric and you can raise and lower indices freely, but when you don't have a metric, they're really different.
Assuming at this stage there is no difference between Q1 and R.
Between which, sorry?
Q1 gauge group and R.
Yes, so there will be a difference. I mean, this issue we were talking about projection and invariance, will play a role in a minute. You want to be very careful. Okay, so how do we impose invariance? So we introduce a new field. Chi of 3 minus 1 and corresponding operator C of chi is the evaluation of chi at 0. And this is of degree 1. So we also have derivatives and derivatives of these operators. So chi is going to represent gauge transformations. So d of chi is A. Because A varies by gauge transformation by d of chi. Because we're dealing with an abelian gauge theory. So thinking about operators, we must have the dual formulation. If I take a function of A, it varies by a function of C. The RST differential applied to operator OI is going to be, well, if I take the ith component of this guy, it's going to be the derivative in the ith direction of this field. That's going to be dxi. Okay. So the full algebra of operators it's going to be a tensor product of a symmetric algebra on 4n join dx1 up to dxn. So these generators correspond to the operators which measure some derivatives of one of the components of the gauge field. And I'm also going to have an exterior algebra. And these are the operators which measure some derivative of the generator of gauge transformations. And the differential is defined on the generators by E, BRC, of an arbitrary derivative of O sub I is equal to I, I. So I just increase the number of derivatives by 1. Okay, this, I feel like things have got a bit confusing. How are people feeling about this?
Can you just quickly repeat repeat why d bar st of OI is dxi c?
Yeah.
I just missed that.
So, yeah, that's an important point. So OI is a functional of the gauge field, which takes its component. And this BRST differential is supposed to measure the failure of that to be gauge invariant. How does that function transform when I change my field by a gauge transformation? So if I apply a gauge transformation to that, I'm going to pick up the derivatives of the gauge transformation. So I get that term. So you can check that, for instance, you expect the gauge invariant operators to be the curvature. So what's the curvature? It's going to be given by something like del I, del xi, oj minus del xj oi. These guys will give you the components of the curvature, and these should be gauge invariant. Because if I apply the BRST operator, this guy picks up the j derivative of c, this guy picks up the I derivative of c, because partial derivatives commute, 0. Yeah?
Is this complex you wrote down the fiber of the local observables at 0?
Yes. Yeah, but we're not imposing the equations of motion yet.
Right.
But yes.
Once we do that, once we
Yeah, exactly. Once we introduce the anti-fields, we'll get like that. Okay, is everybody ready to move on to the final step of putting the gauge invariance and the critical locus together? Yeah, sorry, before I do that, I just want to mention one point that Eugene raised. So I said U1 or, and so far it doesn't look like there's going to be a difference. There actually is a difference. In the case of U1, we shouldn't talk about C by itself. We should only talk about the derivative of C. Let me just look down here. For a compact gauge group, we do not use C, only the derivative of C. So C is what imposes gauge invariance for constant gauge transformations. And these are the things imposing gauge invariance for non-constant gauge transformations. So to do gauge invariance for the constant gauge transformations, because these form a compact group, we just project the gauge invariant operators. And then project operators. Variant under a compact group of constant transformations. So in mathematics, this kind of thing is called relatively algebra cohomology. It happens when you have a Lie algebra which contains a piece which is integrated to a group. And then you take actual invariance for that group and homological invariance for the rest. And like in practice, this is important. So, you might want to compute. There's something called the supersymmetric index, or the supersymmetric theory, where you compute the space of local operators, and you look at the character of its cohomology. Now, if you use this prescription, you get the correct answer, and if you don't, you get 0. So it's really essential to use this. Now suppose we have V, a vector space, and some function, polynomial, and an action of a group on V, and correspondingly algebra. So, when we want to model the critical locus of S inside quotient. We want to do this in some homological way. So we know how to do this. So what we'll do is we'll take our homological model for the quotient and then add on extra variables of the opposite parity to form the critical locus. So before we had the quotient, we could model the critical locus by introducing an antifield for every alpha field here. And now we do the same, but including the ghosts. So here's how it works. V mod G is modeled by polynomials in the xi's and c's. So we introduce psi i's, which are fermionic and degree -1, and B sub A, if taken a string theory course, or like you'd be familiar with the BGOS, these are bosonic of degree -2. And recall that C sub A is fermionic of degree 1. So this is the antifield to this, and this is the antifield to the x's. And the sum of the degree of a field and antifield is always -1. We have the BV anti-bracket, xi psi j is delta ij, and similarly, BA CB is delta AB. So what we're doing is like treating this guy as functions of some supermanifold and just imposing the critical locus function by passing to some cotangent function. So, what's the differential? So it must include it must include the term which is given by the bracketing of S, which is del S, del xi, del psi, because this imposes the equation's critical locus. And it also must include a term which imposes gauge invariance. So I'll just write out the formula for the differential. And then we'll kind of think about what it means. So the full differential, I'll write it as dv differential, or sorry. Q is given by the BV anti-bracket with something which is a sum of two terms. The first term is S, it's a long formula, so let's ponder it for a bit. So this is the one we had before. So what's this term? Remember, the Lie algebra generators acts by the vector fields sum Fia of x d by dxi. And also the bracket of psi I with anything gives, well, that bracket is d by dxi. So this term, once I take its bracket, will give me this differential, plus other stuff. So let's just kind of compute what we find. So so the very first term we want to compute is what happens if we plug in xi? Well, xi only pairs with psi. So qxi is c a f I x. This is the correct thing we want, so this imposes gauge invariance. Q psi I. So we want Q psi I to cut out the critical locus. So if we imagine putting a psi I in there, remember that the x's pair with the size, and s is a function of x. So this will have two terms. S xi. This imposes critical locus. There'll be another term. Well, what's the other term? We know the size must themselves transform under the action of the gauge group. So the other term tells us we don't want to look at all size, just the gauge invariant operators. So the second term comes from the fact that size might pair with the f's. That extension there. Maybe plus or minus c a del x I f j a x psi j. Make sense? So for example, suppose these functions f were linear. That means we had a linear action of our gauge symmetries. The size would transform in a linear representation too, the dual representation. And this thing would say Q acts on the size by some matrix. Like the dual matrix of how it acts on the x's. So this is really taking the gauge invariant functions of psi. Q C A C as usual. And then there's a term involving B as well. Any questions about all this? Does it feel a bit made up?
Yeah, so for instance, like, can you characterize that action functional as unique and satisfying some properties, or not unique, but like at least satisfying some
Yes. So
properties?
yeah, that's a great question. So this involves like some more abstract homological algebra. So this derived quotient, we'll view this as a kind of DG manifold. A derived scheme like that. Then we can look at the derived critical locus. Of S on this quotient. A is given by this shifted cotangent model with some differential. So forming derived quotients and derived critical locuses, these are all operations one can do in the world of DG manifolds or derived schemes. So the point is, this derived critical loci are always shifted Poisson, or indeed shifted symplectic. Shifted symplectic DG schemes or DG manifolds. So once you convince yourself of this, well, because it's symplectic, the differential must be the Hamiltonian vector field for something. The differential must be some Poisson bracket with something, and that something is the BV action. So giving yourself a differential graded shifted symplectic manifold is the same thing as giving yourself just a graded symplectic manifold with a function on it, satisfying the classical mass. So this function, this is a more geometric way to do it, and that's a more kind of formula-based way of doing it. But the invariant meaning is. Okay, any questions about this? So I think we should do an example. So I want to do the example of one-dimensional gauged quantum mechanics, and we'll see why it produces the symplectic quotient. So I'll see how far we can get. I'm not sure this will be too lengthy. You know what? I think this example might be a little bit too lengthy. Time remaining, so maybe I should do a more standard example. Let's do the example of abelian Yang-Mills theory. Suppose we study abelian Yang-Mills theory and we want to introduce fields, ghosts, and all of this. What we've done, what does the algebra of operators look? So we start as before. We have field A, which is a one form. This is a degree 0, and something generating the gauge transformations. And then we need to add antifields So there's going to be A star. This is an n-1 form. 1 and chi star. So I've written things so that the symplectic pairing is just given by wedging and integrating. So we can ask, like, what operators do we have? Like, what local operators do we have? So there's O, I, A, which evaluates the ith component of A at 0. And of course, there's the derivative of that guy. And there's C, which evaluates this guy at 0. There's also functions of the anti-field of A. So what will I call those? So we can index them by an n-1 form, or we can use Hodge star and index them by 1. I'm not going to be too careful about raising and lowering indices. And there's also E. So the homological degree of these guys are 0, 1, minus 1, minus 2. And for each operator that I listed, we also have all of its derivatives. So you can evaluate any derivative of our methods. So the next thing to ask is, what is the DV operator? So in this case, it's going to be very simple. So typically, if we had a non-abelian gauge theory, there would be terms which took an operator to a product of 2 or more operators. Here, because it's an abelian gauge theory, and the kinetic term is quadratic, every term will just take one of these operators to just an operator again. So the formula, if we work out what we had before, OI gets sent to the derivative of C. Well, this NI operator, this is built from the antifield of A, so this really better impose the angles. So it's going to be given by thinking about what's the component of B star D. So what does that look like? That's some second order operator. Sorry, I'm not very fast at thinking on my feet. So one term will be the Laplacian, but I can't sorry, I'm moving it slow. You guys remember the formula?
It's probably a term where one derivative contracts with the index of O, and then there's a I index of the derivative of that. But I don't know what this is.
That sounds good. That?
Yeah, but I don't know if it's a plus one.
Okay.
I think it is minus because it needs to be transposed. Oh, yeah, that's true.
Minus sign?
Yeah.
Okay.
And then the coefficient should be the same.
The which?
The coefficient should be the same.
Okay. So this here to say that this describes the image of this guy will be those functions which vanish from the solutions of the Yang-Mills equations. And now we just need to figure out what B is. And it turns out that this is that. And so this we can figure out by looking at this formula. So in this formula, we're in a case where the action is by translation. We're just taking a gauge field and shifting it. So the F's are constant. So if we look at that formula, there's a term where C interact with a B and produce an antifield. So there's something where B gets sent to an antifield, which is what's happening here. And, and the reason there's derivatives is because there's derivatives, space-time derivatives in that term, because that term is related to the gauge transformations of the abelian gauge. Okay, so I should stop and sec. Any questions?
How do I'm still confused. How do you choose QB equals QPI?
Well, I said you can derive it from this expression. So let me maybe write that out. So the fields and antifields form this. I'll write out all the fields and antifields, then I'll write out that action, and then you can write it. And the full BV action, this guy's called chi A star, chi star. So we'll just look at that expression. The first term will be the Yang-Mills action, which we'll write as A wedge B star B of A. And then the second term, there'll be no third term because it's an abelian gauge symmetry. The second term will be that term there, which tells us about the gauge transformations. So it only depends on chi A and A star in general, but because because we only translate A, the second term only depends on chi and A star. So just integral of chi, right like this, E chi wedge A star. So notice that if we do the symplectic pairing, A star contracts with A and produces B chi, and that's the gauge transformation. So that's how we know what this term is. Now, if I consider SBV, bracket with a linear function of chi star, well, I'm going to be using this term. But by integration by parts, I can write this as pi by p a star. Then I contract that and that with these speeds. Okay. So I often find it convenient to think about this complex. Where this guy does the gauge transformations, the kernel of this map is the equations of motion. So the cohomology here is the solution to the equations of motion modulo gauge transformations. And the rest of it is kind of determined by the fact that this differential is compatible with the pairing, which pairs this and this and this and this. So the operators are just, they live in the dual of this complex. Dual, so I take, a function of here, I'm going to use some kind of distribution like a delta function, and here there's a delta function with some coefficient given by the one-form index, and the differential goes the other way. It's the dual complex. Then they need to slide to that formula. And so next time, then I think we'll do the example of gauged quantum mechanics. And we'll see, that will lead us to the Hamiltonian formulation of BB.